All right. Hey, guys. It looks like we're now live. Okay, everybody out there and in here, I'd like to welcome you to Ultralytics Live Session 18, where we're going to be exploring computer vision at the edge. We're joined by two special partners here from STMicroelectronics. The first is Nicolas Gaude, an AI marketing manager at STMicroelectronics Solutions team. It's focused on democratizing AI and microcontrollers, where we have, I think, a lot of overlap with the team here at Ultralytics, where we also pursue the same passion for everybody to be able to use their models right where they want them, right on the edge, and run all their inference on their own without needing the cloud providers. Also, Mahdi Chtourou, he's a computer vision engineer at STMicroelectronics, and he's specialized in training and deploying models optimized for edge devices. So Mahdi's going to give us a really cool demo a little later on for running YOLO on super low power MCUs that STMicroelectronics has. And Nicolas here is going to kick this off with a brief intro on STMicroelectronics, their efforts in the acceleration of YOLO models at the edge, specs on the hardware, and really, I think the benefits of being able to run these amazing models on super low power devices. Something you couldn't do just a few years ago, but now is being enabled by a lot of these amazing companies like ST. So I'll kick that over to you, Nicolas.
Yes, thanks, Ben. Hi, everyone. Extremely happy to be with you here today. So yeah, let me give you first a high-level introduction of who we are at STMicroelectronics and what we are doing. And then I will also explain what makes us unique when we are talking about edge AI. So first, about STMicroelectronics, for those of you who don't know us, we are a semiconductor company, one of the biggest semiconductor company in the world. And we are basically designing our own electronic products, but we are also manufacturing them in our own facilities. We are more than 50,000 employees over the world, and we have 14 main manufacturing sites as well. And the idea for us...
You're not a fabless house. You actually make the hardware too.
Yes, absolutely, definitely. So we design the microcontrollers. If I speak of microcontrollers, we design them, but we also produce them in our manufacturing plant. And our vision really...
It's a big team, 50,000 people. Where's the spread there around the world? Because I know you're sitting in France, right, Nicolas?
Yes, so myself, I'm sitting in France. We have around 11,000 people in France. So this is a French-Italian company. So we have a lot of Italian colleagues as well. And then we have manufacturing sites all over the world with also sales and marketing teams spread across the globe. Yeah.
Okay.
So we have four main markets for our products where we are really playing. So in automotive, we are looking to making driving safer, greener, and more connected. In industrial, we look like to enabling the evolution of industry towards smarter, safer, and more efficient factories, for instance. Then we have personal electronics, where we want to make homes and cities for better living and higher security. And finally, for everything about communication, equipment, and computers as well, we want to make things smarter and more connected. And basically in our product portfolio, so which is pretty wide, I should say, we have various products ranging from automotive circuits to analog and power conversion to power transistors, MEMS sensors as well. But what we'll focus today, obviously, is on the microcontroller part, microcontroller and microprocessors, explaining how our latest advancements made edge AI or embedded AI really possible now. But first, I will quickly explain what I mean when I say embedded AI or edge AI. So obviously, I guess you are all very familiar with AI, so I won't go into that, but it all started at the beginning in big servers in the cloud, both for training and inference, obviously. What we will discuss right in this session is more on the inference part and how we are slowly but surely moving the inference from the cloud. Now it is really on the device. So let's imagine a laptop, a smartphone, okay? But also now it is moving even closer to what we call the edge, even closer to the sensors in very tiny, cost-effective, power-efficient microcontrollers.
But when you say power efficient, like what's a typical draw on this device? Like how many watts are we talking
Yeah,
about?
okay, that's a very good question. I was about to mention that later, but here, so what you see on the screen is not like a fake image, like generated by AI, okay? But this is a real microcontroller. So you can see that it can be as small as 1 millimeter by 1 millimeter. And the typical power consumption for these microcontrollers, so obviously it will depend on how powerful they are and what kind of use cases you use them for. But when we are talking about edge AI, and in particular the STM32N6, which is our flagship product that I will introduce later, we are talking about, let's say, hundreds of milliwatts of power, and for sure less than 1 watt. Okay.
Okay.
So obviously, when you compare that to big servers, which are gigawatt of power, or even laptops, okay, which are consuming a lot more than that, it's very more power efficient. Also, we are not talking about the same use cases, and we will see that, but there is definitely room for embedded AI.
Yeah. Or on the GPU side, we were recently looking at some of the RTX Pro 6000s that are pushing 600 watts per device. So this is about 1,000 times less or more. Really impressive.
Yeah, absolutely. So that's really, and that's the point of this slide, actually. That's really the benefits, one of the benefits, at least, of what we call edge AI. And the idea here is, as I said, to move the inference part of AI from cloud, connected cloud, to edge devices. And the benefits that you can get from that, obviously, are ultra low latency, because you are computing the data with the neural network model directly within the device. So you don't need to send the data to the cloud and to wait for the answer. So that makes it much more responsive. Privacy and security. Again, you are not sending any data in the cloud. You are processing everything on the device in which you acquired the data. So you don't risk to get your data compromised during the transfer to the cloud, or even in the cloud. Sustainable on energy. We just discussed that with Glenn. The amount of power we are talking about here for processing the data is extremely low as compared to what we usually need for artificial intelligence. And finally, the cost of inference, because if I should mention the cost of such devices, we are in the range of, let's say, a few dollars, ranging maybe up to $10 or $15 maximum, which again is very different as compared to servers, laptops, and so on.
Mm-hmm. Nicolas, I got another stupid question. Would this type of MCU replace an existing MCU, or is it specialized for inference? Is it a type of inference accelerator that would take inference jobs in addition to the existing microcontroller?
No, absolutely. The goal here is not to create a new microcontroller that would sit just next to the other ones. The idea is really that we'll enhance the actual microcontrollers with AI features and AI capabilities. So basically, you can now imagine the same device, which is already in production and you may have with you, but the next generation that our customers will produce, they will integrate this microcontroller instead of the old one, and all of a sudden, we will get some AI capabilities.
Yeah, so the component cost is low, but in addition to that, it's already replacing existing spend for another component. So
absolutely,
very efficient number of ways.
And for those of you who are familiar or who know STMicro and STM32 microcontrollers, we have a huge ecosystem. We have maybe the biggest ecosystem when we are talking about microcontrollers. And what is really important is that this new microcontroller that I will introduce now is fully integrated in that ecosystem, meaning that all the developments that people have been doing for years now, they can definitely leverage them as well.
Okay.
So a few examples of what we are talking about here, but I will be very brief because Francesco will also discuss that a little bit. But this is our typical application from our customers: home appliance with door lock, AC systems being controlled by artificial intelligence, personal electronics, healthcare as well, smart cities, and for all the use cases that you can see on the right. So the famous one using computer vision, people detection, face recognition, human gesture recognition, but also some more fancy ones, I would say, like battery management system, arc fault detection in solar panels, etc. Obviously not based on computer vision, but very nice use cases anyway. But all that also, we have to be fair and say that it comes with some challenges, because Here, we are not talking about devices with a lot of computing power. We are not talking about devices with a lot of memory. And so it will also, Edge AI will also bring challenges. So first, in terms, exactly what I just mentioned, memory footprint of the model, inference time, because if you need extremely fast inference time at extremely high resolution, for instance, okay, maybe there will be a challenge now. Power consumption, we don't have an unlimited power consumption on the device, so that may be a challenge as well. But since the device is very small and very consume very few power, actually we don't need power dissipation. So that's also a trade-off that has to be taken into consideration. And it also brings some challenges more on the data science part, I would say, because the data that you are using today to perform artificial intelligence in the cloud and the models that you are using today in the cloud, they may not be fitting, they may not be the right ones for Edge AI. And this is why it is extremely important what we discussed today, how by the collaboration that we have between Ultralytics and STMicroelectronics, we are now enabling these computer vision AI use cases on the device directly.
Mm-hmm. This is what I love about AI. It's been a long time since the theories were proposed in the 70s. The software and the algorithm started catching up in the 2010s and the 2020s, and now the hardware. So it's the synergy of both that's coming together to really enable these awesome capabilities.
Yes,
we're
absolutely.
Right here, like in the middle of the party. So it's an exciting space.
Yeah. And this is really one of the biggest challenges that we faced at the beginning of Edge AI, because a lot of people have already been doing AI, as I said, using cloud and servers. But then they try to fit 1 gigabyte models or several hundred megabyte models in these tiny microcontrollers, and nothing is working, right? So It's really about how do we guide everyone who is looking to leverage Edge AI for their product, and what can we propose to make their life easier.
Mm-hmm. Yeah, completely different environments. Yeah.
And speaking of that, so on one side, we have Ultralytics and the YOLO models, which we all know are extremely optimized, extremely well-performing for computer vision. And on the other side, on the ST side, we have this STM32N6, which is our flagship microcontroller, the latest one that we have, and which is actually the first one with a neural processing unit, so an AI accelerator. Basically, I will explain that for those of you who don't know about that. So yeah, speaking of NPU, maybe most of you are already familiar with that, but what is an NPU? So the NPU stands for Neural Processing Unit, and basically this is a processor which is optimized and dedicated to accelerate neural network models and AI operators and layers. So you can think initially when GPU were introduced, they were optimized for graphics, anything related to graphics, right? And you can think about NPU. It's a similar processor, but instead of being optimized for graphics, it is optimized for AI. Today, GPUs are also used for AI, because we some years ago we discovered that they can process data in parallel in an efficient way. But here, this graph is really just to show you that the difference between NPU and GPU when it comes to efficiency, or the way they can process images per watt, right? And these NPU, these dedicated processors for AI, well, we can now use them not only in laptops and smartphones, because some of your laptops and smartphones have them, but also in microcontrollers. And this is what we have in the STM32N6. And if we have a quick look at what it brings in terms of performances, so here you see a benchmark that we did on the STM32N6, so our latest microcontroller using the neural processing unit, as compared to a typical microcontroller that you can find here out in the field, And we picked very, I would say, standard neural network models for various use cases, image classification, object detection, audio recognition, and we computed them on both processors, and this is the type of acceleration ratio that you can get from the NPU. So again, just to illustrate how this type of new devices now enable real-time performances directly on the device.
These are huge leaps.
Yes, and so very quickly, what can you get out of that? So obviously you will get performance, but it's not only about performance. It's more, from this same microcontroller, now that you are using the NPU, instead of working on a single modality, you can use multimodality networks, like working on audio and vision at the same time. You can move from low resolution, like, I don't know, 96 by 96 to higher resolution, 416 by 416. The frame rate obviously will go higher. You will see some numbers later on YOLO V8, and we have real-time inference using these models. So obviously it will bring performances, but it will definitely broaden also the type of use cases that you can target. And two last slide. First one about the N6. Obviously, it has this very nice and very well-performing neural processing unit, but it also has, as you will see later, very nice graphics and multimedia capabilities. The chip itself, it embeds computer vision pipeline, it embeds multimedia encoding and decoding, so making it really the perfect solutions for anyone looking for edge AI computer vision type of use cases. And now, this is my last slide, and then we will move to more technical part. But it is extremely important to also understand that a good hardware, you can have the best hardware, but if you don't have the software stack that come with it, it's barely usable. So here the idea is that we also developed, to come along with the STM32N6, we developed a full development ecosystem for AI with first, and this is what Mahdi will show, our STM32 Model Zoo, which is a GitHub repository of models and scripts to deploy AI on the microcontroller. We have an online platform that we call the STAGI Developer Cloud, which basically you log to this platform, you can upload your model, and you can compute in just a few clicks the real performance of your model using STMicroelectronics And then we have the STAGI core. You can see it, so this is a command line interface, and you can see it as really a compiler for the STM32N6. Because if you want to efficiently map your neural network model into the hardware, you need a compiler that will do this job. And this is exactly what the STAGI core is doing. And again, Mahdi will use that during his part. So that's it for me for the high-level introduction. And again, I think we'll move to more funny stuff with the technical part.
This looks good, Nicolas. So ST is not just investing in the hardware, but also the ecosystem, which I'm a big fan of, making sure that developers can use the tools, have support in the community there to help them when they run into problems.
Yeah, this is extremely important because historically our users, they are embedded software developers, okay? And they are not extremely familiar with data science and AI. So we need to make sure that these guys, they can develop AI applications smoothly on our devices. And at the same time, we need to make sure that data scientists, they can get started with our product fairly simply.
Yeah. Thank you, Nicolas, for the presentation. That's super impressive. On the Ultralytics side, we can say that this is impressive because I've never seen a device so small that can run a YOLO model, and this is really impressive. So this is in particular, this is an MCU, not actually a microprocessor. So that means that doesn't need any boot or any kind of software component. You can directly fetch the network with your software and you turn on and it is going to work. And this is impressive. So
actually, Francesco, I was about to ask a stupid question because I've always been confused about, there's a few words that people typically associate that sometimes I think they replace with each other. But so in terms of an ASIC on a PCB or an MCU or FPGA, like I saw you had in the slide, Nicolas, so could you explain a bit really like what an MCU is and how it differs, I think, from the rest of the chips that would typically be on the board?
Oh yeah, absolutely. So something I haven't mentioned in the presentation is that really microcontrollers, they are all around us basically. In any electronic devices that you will use, it can be a USB stick, a remote controller, a smartphone, obviously, a car, you have microcontrollers everywhere. And so what I have shown in one slide, this very tiny chip, this is what we call a microcontroller. But then when you want to do a real product, you will need to integrate that into your product. And the way you see it is that you will create what we call a board or a PCB on which you, integrate the microcontroller plus some external memories, maybe a camera interface. You want to add some USB connectivity as well, some on top of the camera, you want other sensors like accelerometers, microphones. So you put all that on the PCB, and you can get like, I don't know if you will see it with the background, but this is a camera that has been produced by one of our partners. So you see it's extremely small. It's maybe 4 centimeters by 4 centimeters. And in this camera, actually, we have one STM32N6 with memories, with the camera module, with other sensors. And basically, our customers, this is what they will looking to produce. They will be looking to produce and then use that for their end product.
Okay.
So just to clarify, Nicolas, so then your customer basically buy the actual chip itself, and they basically build the carrier board that is going to embed this chip, and that's it, right?
Yes, absolutely. So we, again, I have one slide for that at the end, but let's do it now. This is, I have another board here. Sorry for the blurring.
It's a screen on the back of the PCB, right?
Yeah, so this is what we call a discovery kit. So the idea of that is that you can, for people willing to try and perform and develop some applications on our microcontroller, they can take that, they can buy it as is, okay? It comes with the STM32N6, which is soldered here on the back. Then it comes with the big screen. It comes with the camera as well. And they can then start developing their own application. This is only for prototyping, let's say, and evaluation. What people will buy in the end is just the chip itself. And as I said, they will develop their own devices, combining our product with other products coming from other suppliers.
Yeah, fully customizable.
Yeah.
Thank you, Nicolas. Again, I want to go with the demo because that's the real juice of this conversation, the live demo. So I want to just introduce the demo by saying that today, with our partnership, we support YOLO V8, basically all the tasks, except object-oriented bounding box. But for the rest, we support all tasks with the nano model. And we are also actively working to support YOLO 11N. Just my 2 cents is that this is really impressive because this small device that have a power consumption of 225 milliwatt, I just read the benchmark table, this is impressive, can run a YOLO V8N with 256 by 256 images with a so low power consumption. And this basically opens up a lot of possibilities. Means that we can run this device battery powered for days. And we have shown this during IoT World Congress, where with Nicolas, we show a demo of the device that Nicolas just showed you that runs basically days battery powered with a YOLO V8N in real time. In terms of use cases, this opens a lot of use cases. You can, for example, think about devices that you can place in a remote position, like in just thinking about forest for detecting wildfire, for example. You don't need to have energy there, direct energy, but you can just place this device, collect and analyze an image every 10 minutes, and with battery power, it can last for months. Even So this is impressive. And this really opens up a lot of possibilities. We have evidence of clients using this for a lot of different use cases in urban environment, like for pedestrian detection, for vehicle detection, for smart city infrastructure in order to determine some parameter to actually act directly on the infrastructure, on-device safety checks, like in automotive sector, but also in industrial automation and quality control. So I want to leave all the space to Mahdi to show the demo. Just want to do a quick introduction to just have an overview. So today, in order to basically generate a model, you can use the Ultralytics repository to basically export the model in TF-Lite format using int8 quantization. So you can train your own model, export the model, and then STMicro offer basically a converter that allows you to basically deploy the device, compile the model to actually deploy the model on the device. So I'm going to leave the stage to Mahdi. That is going to have a super cool demo.
Okay, thank you, Francesco. So indeed, we will see together how to export YOLO V8 model using Ultralytics. and then how to deploy the model on the STM32N6 board using the STM32EI model zoo. So I'll share my screen to see together how to do that.
Yeah, I want to anticipate that we have a lot of questions. So let's leave at least 15 minutes at the end because we have a really bunch of questions.
I think I have a lot of questions too, but I'll try and keep them to myself so we can get to the user questions.
So the two projects are the Ultralytics GitHub and also the STM32EI Model Zoo services. This is all what we need to deploy Ultralytics models on the STM32N6 board. To export the model, we will start with the Colab notebook provided by Ultralytics. I have it open here. So as usual, we will need to start with installing the dependencies of Ultralytics. It should not take long.
While we wait for that super exciting piece of news, we just passed 100 million downloads right there. It says 101. So it's a huge milestone for us. We launched the package in January 23, so it's taken like a little over 2 years to get here. But I'm super excited about that.
That's very impressive.
Nice. Next to Ultralytics dependencies, we will also need to install some ST deployment environment dependencies. It's mainly about TensorFlow version to make sure that the exported model will be compatible with ST EI environment.
Okay.
So we will install these dependencies. As you can see, it's mainly about TensorFlow version on NX, also the version of on NX and on NX runtime.
By the way, something I've been using lately for super fast pip installs is UV. It works amazing. I think it sometimes works in Colab notebooks out of the box. That's the reason we don't default to it. But so it's great for faster installs, especially for large packages.
Yes, indeed. So for the model, we will try to quickly train a model on a subset of Coco. And we will try to work with the YOLO V8 model, but we can reproduce or execute the same steps to generate a YOLO 11 model and deploy a YOLO 11 model on the STM32N6 board. But for this exercise, we will stick with the YOLO V8 model. So we will train quickly a model for a few epochs. Here I'm training on a subset of Coco for 3 epochs, but for sure the user can bring his custom dataset and train the model for more epochs to have some probably decent results.
Yeah, and I think this answers one of the questions that I saw over there on YouTube, which is, are these actual official models that we're deploying, or are they some sort of like smaller, later, like cheaper model? And so this is the actual official YOLO V8N model right here. We're starting from the official pre-train checkpoint. And then, of course, this is just an example of fine-tuning. Here we're fine-tuning on our Coco 8 data set, which is a super tiny 8-picture data set just used for examples and so on. But this could be any data set, your own custom data set, and use that official architecture.
Exactly. So after training the model, we'll try to quantize the model and export it.
We almost didn't notice, but it trained in like 2 seconds. It's because the model's small.
It's already quick.
Yeah. We've done a lot of work to make everything fast in the Ultralytics package. So, yeah.
It's a quick process. And also, we should not forget that we trained the model only for 3 epochs. But for real use case, in
the real world, you're going to want a few more epochs, a slightly bigger data set, and so on. But this is really just to get the picture and as a proof of concept, really. So if this passes with no errors, a larger data set and so on should also work without error.
So after training the model, we will try to export the best weights into TF-Lite format, but also this TF-Lite model should be quantized. Why quantized? Because the N6 is optimized to perform better with the quantized models. So this is very important. It's important to quantize the model to get the best performance. To export the model in quantized format and in TF-Lite format also, we just need to specify the format as TF-Lite, set the int 8 to true, and to get the best trade-off between accuracy and inference time, we will select the input size of the exported model to 256. So usually, if we use a smaller input size, we will have better inference, but probably less accuracy. And if we use a larger input size, we will get better accuracy, but less inference time. So using this command, we will be exporting the model.
I love Colab because anybody can just click the button and even my mom can models like this.
Yeah. Life is easier with Colab. So as you can see here, we are using the TensorFlow version that we specified to export the PyTorch model to TF-Lite model. This is very important. The process takes few seconds. It will not last long.
Yeah, and I see we're doing a slimming operation, as it's called. We used to use Onyx Simplifier package, but it had installation complications on some environments, since I think it needed compilation steps. And so we've migrated now to Onyx Slim, which is a great package, Python native, and works just as well in slimming down Onyx files, removing those extra operations that aren't strictly necessary. So we've got a bunch of console output here.
Yeah,
so these are intermediate steps for debugging.
Yeah. So the export finished successfully. We can find the exported model under runs, detect,
chain, and then weights.
And
oh no, the actual exported model, it's go back.
I think it's in the train directory, actually. Yeah. This is train 2. So if you go to train, let's see, so that is not opening up.
You have it on runs, on the runs folder, and then
detect,
detect, and
then train. But there's nothing when you open up there for train.
Okay, under weights, hopefully.
So let's see. So the console output here says
it's under train weights, so but it's not.
Oh, I think you might need to refresh the files, actually. Maybe click that refresh button. And now try to open train. It's definitely there because it's got a file size. So it says TensorFlow Lite, 3.2 megabytes, which I think lines up with what you'd expect for a nano-sized model, which is about 3 million parameters at indate.
Yeah, can you try to rerun the shell, please, Mahdi? Maybe,
sure.
Maybe this is the old output. Maybe you really actually.
It's there actually.
Oh, okay.
It took some time to refresh, but it's there.
What did you do? I was just talking about how great it takes like a 30-second delay for the files to render. All right, so we've got a range of files at different quantizations here.
Indeed. Yeah. So there is a bunch of files, all of them TF-Lite files that were generated by the export task. But what we will be interested in is the full integer quantized file. So this is what we are going to download. And after downloading this file, we will move now to the other project, which is the STM32EI model Zoo.
Yeah, of course, if you are using your own environment, you don't need to download anything. It is going to be in your file system already.
Indeed. For this exercise, we use Colab, but if we install the package on our local machine, we will not need to download the file. We will find all the folders and generated files on our machine.
Without 30 seconds of delay, hopefully.
It depends on what kind of computer you have.
Yeah. So for the STM32EI Model Zoo surfaces, we have different use cases: classification, segmentation, pose estimation, object detection. And since we exported an object detection model, we will see how to deploy the object detection YOLO V8 object detection model using the object detection use case. Here we will find a README that will help us to go through the deployment task. But before we start, of course, we will need to have the STM32N6 discovery board and make sure to connect it.
That's the one you were showing before, Nicolas.
Yeah, Nicolas, quick question. They are asking for the prices. I have seen a couple of comments asking for the price of the discovery board.
Yeah, so this is fully available both from ST and from regular electronic distributors. The price of this kit is like $180 roughly. And as I said, it will come with the chip itself, the display, the camera, the memories. So really, you just need to buy the kit and you got everything you need to get started with your embedded AI project.
Thank you, Nicolas. Very cool board, if I can.
So this is regarding the hardware requirements. Regarding the software requirements, we will need to download and install ST-Edge EI to generate the C network from the exported model. And also we will need to download and install the STM32Cube IDE to build the embedded project. So now we will clone the project and try to do the exercise. Here I already cloned the STM32EI Model Zoo. There is Python requirements, so make sure to create a new environment, probably a Conda environment, and install all the requirements in this file. And now we will use the object detection use case to configure the deployment environment in order to deploy our model. So for that, we will open VS Code. We will navigate into object detection. And here we will find a YAML file called the user config. This is the interface between the user and the deployment task. So if we open this YAML file, we will find a template, a generic template that offers us a lot of options. As you can see here, for the operation mode, we support different tasks: training, evaluation, deployment, quantization. So I encourage the users to check the documentation to understand the different services. But for this exercise, we will use the deployment operation mode. So we need to configure this config file to use it. I prepared a template to not spend a long time updating this file. So we're going to use this template. The template can be found under source, config file example, and YOLO V8 deployment on N6. So we will copy the content of this file and paste it under user config. Now we will go through the parameters to explain them a little. So under the general section, we will need to point to the model path, the model that we trained quickly and downloaded, quantized, export, and downloaded. We need to precise the model type. We support different model type, including YOLO 11. So also I encourage the users to check the documentation about the different supported model types. It's important also to set the operation mode to deployment. For the dataset section, since we trained the model on Coco dataset, we need to precise the classes names of the Coco dataset, which it's a list of 80 different class. This is the pre-processing and post-processing that will be embedded in the application. So here, for pre-processing, we have some resizing parameters. For example, if we want to keep the aspect ratio or not. Also, we can choose what kind of interpolation we want to use, nearest or bilinear. Also, it depends on how the model was trained. We need to precise if we are using RGB images or BGR images. As we know, for object detection models, most of them need some post-processing to be to filter the detections. So this is the post-processing parameters, including the confidence threshold of the detections that we want to keep, and the non-max
non-maximal
suppression,
suppression threshold.
non-max suppression threshold also. There is also a parameter in the post-processing, which is the max detections, max detection boxes, and actually it will allow the user to limit the detections that will be displayed on board. You can put 5, and even if the model predicts 10 detections, you will see only 5. This can be useful in some cases. So for the tools section, we need to specify the ST-Edge version. We recommend, of course, using the latest version. For the optimization, there is different optimization options. There is the balanced, and there is some options to accelerate the inference time, and some options to optimize the memory usage. Also, all this available in the documentation on the model zoo. Now, for generating the C code of the deep learning model, we need to precise the path to ST-Edge that we already downloaded, but there is also another option. Instead of using a local installation of ST-Edge to generate the C code from the model, we can use the on-cloud option. We can set it to true, and in this case, you can connect to the REST API, and the C generation of the network will be executed online, and then the files will be automatically downloaded, and then they will be integrated into your C application. But for this exercise, we will use the local installation of ST-Edge. The same. Yeah.
Can I ask you something, Mahdi? Sorry for interrupting. Is that, I mean, it's a free tool, the one that allows you to basically do the compilation online, or it's a...
Yeah, it's all free. All what you need is ST account. It's a free account also to create. And it will allow you to do the exercise online, the exercise of converting the network to C code.
So that means that users are able to basically go till there and even compile the model without actually having a device. That's super interesting.
Indeed.
Okay. Mahdi, stupid question.
Yes.
I see you're a Windows guy, and I think Francesco here too. What if you're not? What if you use Linux or Mac OS? Does this work there too, or do you need to run this on Windows?
Yeah, so we have different builds for different platforms. So we have ST-Edge build or release for Windows systems. We have ST-Edge for Ubuntu systems, and also we have for Mac systems. So
okay.
Awesome.
We have different releases for different platforms.
Yeah, I see. Okay.
Same
These
for
YAML would look identical. We would just modify lines 26 and 27, basically.
Exactly.
Okay.
So the same for Cube IDE, which is used to build the project and flash the board. We need to precise the installation path of Cube IDE. Finally, for the deployment board, mainly here we need to precise the board that we want to use for deployment, which is in this case the STM32N6 discovery kit. Okay, so we are almost ready to execute to run this script and flash the board. But one small detail, but it's very important. Before flashing the board, this is the STM32N6. It's important before flashing the board to switch to push the boot switches to the right before flashing the board. These are the boot switches. And after flashing the board, we need to push back the boot switches to the left. So this is important to have a successful deployment.
So this is basically for setting the flashing mode, right?
Exactly.
Okay.
So as you can see in the README, the deployment README, there is all the details. I encourage the users to go through the README and understand better the process. But what I mentioned should be enough. Okay, so we can now just run the following command, and it will start the task of building the project, automatically building the project, and then flashing the board. Can wait a little.
Yeah, so maybe while it is doing it, just to summarize what we are doing here, Mahdi, is that we are taking the freshly exported model from Ultralytics YOLO V8, and then we use it with our own tool to optimize it a little bit and compile it into the C code that we then embed into the full application to perform object detection. And this application, this embedded application using C code, again, we compile it into the binary file that we will flash, we will program into the devices itself. This takes a little bit of time, so we will not go through the end of the process, but we will show you what it looks like once it's really programmed in the device.
Exactly. So this may take a few minutes to build the project and flash the board. So I'll stop sharing my screen here, and Nicolas will show you what it looks like, or how the application looks like on the STM32N6 board.
Okay. And Nicolas and Mahdi, to connect your computer to the board, do you use a special kind of emulator for that?
No,
or
so
just
basically
like a USB cable,
board,
or how does that work?
Yeah, this is just an USB cable. On the board itself, you have
just a
USB
cable.
Type-C connectivity. And basically, you connect the board to the laptop, and then you use the tool dedicated to flashing the board, basically. And once this is done, when you will power on the board, it will execute the program that you just flashed, and it will run the application that you compiled.
Okay, so power and data all through the USB-C cable.
Yes, yeah, absolutely.
Nice. Okay.
Yeah, and so as Mahdi said, this takes maybe just a few minutes to fully compile and program the devices. Actually, the compiling part is very, very fast, okay? It's more the programming part, which takes a few minutes. So we are skipping that now, but what I want to show you, because I saw some questions in the chat about the performances that we can really get, is a few, videos that we did directly taking what is happening on the device itself. So let's start with the first one I'm showing is a very typical people detection use case, okay? Object detection trained on person using a person data set. Here, the resolution is 320 by 320, which may look small, let's say, but as you can see on the screen, we can detect people up to, 7, 8, 9 meters with very nice accuracy. So in most of the use cases targeted by this device, this is more than enough. On the right of the screen, you have some performances and some typical application for users for this type of model. Another very familiar use case is the pose estimation, obviously, which is very nice with YOLO V8. Here again, you see the type of performances that you can get from the device. The resolution here is a little bit smaller, 256 by 256, mainly because I can show that later, but if you use higher resolution, you will start using more memory, and meaning you will need memory outside of the chip itself. And when you access these external memories, the bandwidth is smaller, and then it will drop the performance of the application. So if you don't need like real-time operation, 30 FPS, and you only need, 4, 5, 6 FPS, which is the case in some applications, then you can go for higher resolution. Okay, here again, this is object detection. What is nice with this one, at least what I like, this is multi-object detection. Okay, you can see that we detect a hand gesture. So this is YOLO V8N, I should have mentioned it, trained on hybrid data set. and we can detect different type of hand gestures at the same time in the same frame. Okay,
it's really cool.
Yeah, I just want to answer a question. Correct me if I'm wrong, Nicolas, but somebody asked if all the models are quantized, and we can say yes, all the models are int8 quantized. Is that correct, Nicolas?
Yes, that's correct. As Mahdi briefly mentioned, the NPU that we are, so the neural processing unit, the AI accelerator that we are using in the chip, actually works on integer 8 bits data. So if the model itself is float 32 bits, for instance, then it won't be accelerated by the device. So this is what, and also obviously floating point model are much, much bigger than integer ones, quantized one. So this is why we quantize in 8 bits to get the acceleration from the hardware, but also because we have seen that in most of the cases, 8-bit quantization is pretty well supported by the models. And this is definitely the case for YOLO V8 or YOLO models, I should say.
Yeah, I also have another question, Nicolas. Is H.264 encoding, decoding available in the chip?
Yes, absolutely. Absolutely. Good question. So this is part of the multimedia capabilities I was referring to. So we don't have the H.264 decoding in the chip, but we do have H.264 encoding. And this is why, like for, I don't know, doorbell systems, for instance, it's very nice, because you will capture the data using the chip, you will perform the AI inference using the chip, then you will encode the video feed, and you can stream it over Wi-Fi, for instance, or HDMI, I don't know, in a compressed format, yes. And basically, that's a good link to maybe this use case that I can show you, which is performed. So this is segmentation, okay, using YOLO V8 nano model again, which is nice with this one. Obviously, the model is nice, but what you can see on the middle of the screen is the little camera I've shown at the very beginning of the session, which has been developed by a partner of us, E2IP Technologies. You can buy this camera, by the way. I'll show that later. And this one is working either with the USB for power and data, USB-C, or it can work over Wi-Fi as well. And basically, we capture the data and we send the compressed data over Wi-Fi. And this is what you see on the left part of the screen. And maybe a last one, and then we can leave some time for questions. But it is also another use case that I like, which is about automatic checkout and in a smart retail use case. So here we trained, this is not sure if it's a V8, I guess it's a YOLO V5, but it could be a V8 anyway, using the same camera again, and we trained it on fruit and vegetable data sets. And the idea is how we can, well, detect and count fruits and vegetables when you are purchasing them in a store, and automatically counting what you get in your bag.
This is my main dream for computer vision. So when I go to the grocery store, I don't need to figure out which fruit I just put on there. It just recognizes it and then puts a sticker on.
Yes, and most of the time,
we're still working on that, but it's getting close.
Yeah, most of the time when you do that, you need to put the camera, you need a lot of wires or connectivity, you need servers to do. And here you can do everything directly on the device, which is, extremely convenient.
Yeah, this is really cool. I really like this.
Yeah. So since we mentioned a little bit the way to evaluate the product, the STM32N6, this is what we propose today. So the two devices on the left are STMicroelectronics devices. The first one is a very tiny board with reduced peripherals. The cost is also much smaller than what I mentioned before, but it has no screen, no camera. So for people looking for a very simple to use solution with all the peripherals, display, camera already available, this is definitely the one in the middle. Okay, this is the one I was referring to before. And also this is the camera on the right that you can see from our partner E2IP Technology. And this one is very nice for small volume productions. You already have an idea that you want to start producing. You want to do a proof of concept and you need a small form factor camera. This is what you should go for.
Okay.
And also a quick reminder, and then I'm done, about what has been mentioned by Mahdi. What has been shown today is how we use a Ultralytics YOLO model and how we deploy it, okay, end to end from the model to the device. If you want to reproduce that on your end, this is what you should look for. So on our side, this is the STM32 model zoo. Mahdi, I explained that already. You will need the STAJI core, which is the command line interface to optimize and compile neural network model. And also, if you want to get started very quickly, you can go to this web page on st.com, so STM32N6-AI. And on this page, you will find binary file for already ready-to-use applications for object detection, people detection, segmentation. So you need the board, you take this binary, you flash it, and then you're good. You can start playing with it.
Hey, very cool. I'm looking through the questions here on the YouTube side. We got a bunch of them. I think let me jump into one of my favorite questions that I've seen here is what's the accuracy penalty on the quantizations that we've shown? So in ML, like in life, nothing comes for free. And when you reduce the quantization of the weights in the model, you're reducing the number of bins in the digital space that they can occupy from many tens of thousands to just 256 at 8 bits. And so this does have a minor impact on accuracy. It's tough to answer the question directly because the impact that it has depends a lot on the quality of the calibration data set that you supply. So FP16 is pretty much lossless. If you export to that, there's really no accuracy loss. But once you get to int8, then we typically require a calibration data set. If you've exported int8 without supplying it, then we just grab, I think, the Coco 128 data set by default, which is a nice place to get started, but you can do better. And if you provide more images, and especially more images that are representative of your deployment space, so basically your training set or your validation set, if you can pass those, and if there's several thousand images there, then the calibration process will iteratively work on those weights so that the output, the loss is actually minimized. And in the best case scenario, then your accuracy might drop from something like, let's say you started at a 50 map, it might go to say 49 or 49.5. So the performance benefits are substantial. And while there is an accuracy loss, it's quite minor that for most applications is barely noticeable. But again, that calibration data set, pay attention to that. Because if you supply a small one or just take the default one, then I think you'll lose a few percentage. Could go from like 50 to 45 or something like that. So then you might notice the difference.
Yeah, I also have two other questions. One is how to interface with external application. I think that I can answer, but help me, Nicolas and Mahdi, if you want to add something. Basically, those chips are meant to be embed on a carrier board. So depending on your application, you can interface with the actual chip in a lot of different ways, through serial or through a server that you can basically spawn on the device. But if you want to add something, Nicolas, here would be helpful, or to actually interface with the chip.
Yes, so the chip itself, just the chip, it has, a lot of interfaces that are very common in the embedded world. So you have I2C, SPI, serial, UART, a lot of them. All these peripherals and interfaces, you have them obviously with the STM32N6. When it comes to the board itself, so we have already mapped some of the interfaces directly to use with the button, with the screen, the camera, but still you also have a lot at the back of the board. You also have a lot of pins and connectors that you can use to add additional features to the Discovery Kit.
I've got a question real quick, Nicolas. So we've seen a lot of demos at 256 pixels, 320, and this will roughly result in 4 times faster inference than 640. But is 640 inference possible? Like, does the RAM on the microcontroller support that? If we want, say, a lower frame rate, like if we just want to run inference at say 1 image per second at a higher image size, would that work too?
Yes. So I'm just sharing one more slide to answer that. So I don't have the numbers for like 640, but what's important, so here you see various tasks like object detection, pose estimation, segmentation for various resolutions. And what you see is actually how much weight and activation you need for each of these use cases, and what is the performance you can get out of it in terms of frame per second or inference time, whatever. So you see that obviously the higher the resolution, the smaller the FPS, I should say. but still, this is very reasonable in my opinion. It all depends on the use case. If you are on a high-speed production line and you need 100 FPS, that's not the right solution. But if you need to do person detection on a laptop, to turn it off, turn it on, for instance, that's definitely okay. If you go to higher resolution, what happens is you start using the external memory, as I was using before. Here, all these models, they fit within the internal memory of the chip, which is pretty fast, let's say. If you start using external memory, this memory is slower, which means when you need to retrieve the activation from the external memory, you are not as fast as doing it from the internal memory, and then the FPS will drop quite, I won't say significantly, but it will drop, and you will notice that. So maybe if I look at object detection at the first top left table, on 416, I have like 17 FPS. If I go to 520 by 520 and I start using external memory, maybe I'm dropping to 10 or 7. I don't know. I have the numbers, I could check, but this is what the ballpark we are talking about.
Yeah. Okay. Two other questions, Nicolas, and then we need to close, I think. First one is, can you share some consumer device that already integrates the MCU? And the second question, and then I'm gonna answer both of them. Can you connect multiple camera to the device?
Okay. So first one, the device itself was only launched in December 2024, so 6 months ago. We had an alpha phase with a lot of customers already before that, but so the product is in the hands of many customers. It is starting to be used in the field, and the main product use cases that we are seeing is like lawn mowers robots, you know. We also have vacuum cleaners robots, obviously. In some, you know, the gimbal devices to track you when you want to film yourself with a smartphone. Door lock, I mentioned that already as well. We have aftermarket dash cam in cars for driver monitoring systems. So really diverse type of applications, and the product is really hitting the market right now. And on the second question about multi-camera, so we do have a camera pipeline within the chip, which is 2 lanes, I guess. But you can connect, let's say, 2 cameras, for instance, which is the maximum you can connect, I guess. But they would work, you know, alternatively, not both at the same time. So you need to share the bandwidth between the 2 of them.
Yeah, potentially you can even pass the image through a serial communication, and then you can have also a million of camera.
We do have customers. We do have customers which are using RGB camera on one side and other type of sensors like time of flight, infrared, thermal sensors, and you can combine depending on what you want to do.
All right, amazing. So it looks like a variety of use cases you're explaining there, Nicolas, which is what we see also on the YOLO side. It's one of my favorite things about computer vision, that it's not really scoped. There's so much potential in it, so many different things that we can do. My other favorite thing, it's not a question that I saw on YouTube, but it's just some comments, people dialing in from Brazil, from Belgium. You over there in France, I'm sitting here in London at the new Ultralytics office, Francesco down there in Rome. And so this is truly a global community. I think that technology has amazing potential, great impact, and it really brings people together and really democratizes a lot of this potential. So on the software side, which is of course what we work on at Ultralytics, and also on the hardware side with these super low power, affordable ASICs that you can really drop into so many things, as you've shown, Nicolas. I think this is the powerful combination. It looks really awesome, and I think it's going to be great to see what people actually build here. So thank you for joining us here, Nicolas, Mahdi, and Francesco, and thank you for everybody out there. Unfortunately, I don't think we got to everybody's question, and I'm sure there's a lot left. Feel free to drop those on our GitHub, on the ST GitHub, or within our Discord channel, Reddit, really anywhere. Thank you so much, and we'll see you at the next Ultralytics live session. Bye.
Thanks, everyone.
Bye.
Bye.
Thank you.
Bye.